Welcome to Make Me Data Literate, the podcast that makes data intelligible from the Australian Data Science Education Institute. We're on a mission to make the whole world data literate. I'm your host, Dr. Linda McIver, and every week I'll interview someone with a wild and wonderful relationship to data. Let's see what we can find out. Hello, and welcome to Make Me Data Literate. I was accused when I started this podcast of simply creating a vehicle to have conversations with really interesting people, and my guest today is certainly not one to dispel that rumor. I'm very excited to have Professor Alan Duffy. Welcome, Alan.
Well, thanks so much for having me, Linda. And I'm just going to reflect that perhaps I am the exception that proves the rule to that. So hopefully I won't bore everyone, but I can't claim to be quite as fascinating as some of the other people you've been chatting to.
I don't think that one's going to fly, but we'll let the listeners decide by the end of the podcast. Um, I'm going to, rather than try to give you an introduction which does justice to your background, which I just don't think I can do because it's phenomenal, I'm going to just jump in and ask you to explain who you are and what you do.
All right. I am an astronomer by background and a specialism of computational astrophysics, so use of supercomputers to model the formation of galaxies like our own Milky Way and large clouds of dark matter. Uh, the last 7, maybe more years, I've become more experimentally focused to find that dark matter in the lab with an experiment called SABRE that is going at the bottom of a gold mine here in Stawell, Victoria, in the next little while. But I've also, yeah, tried to do other experimental efforts, including maybe we'll get to founding a company. But I think first and foremost, I'm a scientist, but perhaps I'm better known as a communicator. And I like to think of myself as a scientist who communicates rather than a science communicator. And the difference is the latter is an actual career. It is a profession. You get a degree, you get your training, you should be paid accordingly. And the former, the scientist who communicates, well, you know, I get to play around with communicating, telling people what I'm doing. And I think as a scientist who's in the main taxpayer funded, you got to tell your bosses what you're up to, and that's the public in my case. So that's one very good reason I think to go out and try to tell people about the awesome stuff that's going on here in Australia. And it's not the only reason I do it. It's obviously a passion. I love to get other people excited about it as well. So I'm not the only nerd in the room. I want as many other nerds as I can make happen. But certainly from my perspective, it's the science first and foremost, and then the opportunity to communicate it that comes later really is the incredibly thick icing on the cake.
I love that idea that you're making more nerds, and I think that's a hugely important thing about communicating as um, educating more people and bringing more people into the idea that this stuff can be so interesting, and it's not necessarily the way we've experienced science at school.
Yeah, look, it wasn't the way I experienced it. That's for sure. I was reflecting on this recently to a high school student who just wasn't going to pick science at all at uni, and from what I understand, the grades are exceptional at school, and that's because of how it's being taught in their school. And I explained to them that I took physics at uni, despite my high school physics, not because of. And in particular, that was um, not just the teacher in the school. I mean, it's very easy to, I think, bag out individuals. I think that's the wrong approach. You can always have exemplary, you can have inspiring teachers, right, who will overcome the odds to make it engaging. But just the act of teaching rather than investigating collaboratively, that's the difference, right? So when you're at uni, you start off with lectures, there's experimental, but you're actually able to talk to people who are on the frontiers of discovery, and you know that you can sense the difference, and you can be a part of that very quickly in research projects over the breaks, or even just during your units here at Swinburne. Our final year is all around investigating an actual true research project, either here in academia or even with industry as work experience. But so I got a little taste of that, so I was able to sort of get through the high school experience. But I think the mode of teaching and curricula and how prescribed and teach to the test, et cetera, et cetera. I'm sure we'll get into, but it has a lot to answer for, where it can make something as profoundly magnificent as astronomy dull and rote learning and everything else associated that students don't get super excited about, because I think they all start off excited about the world around them, maybe certain areas more their jam than others, astronomy being mine, but I think fundamentally every student is excited or curious about the world around them, and then somehow school beats that out of them.
I think that's really true. And this is not supposed to be an education podcast, so I'll try not to not to go down that
Yeah.
rabbit hole too much. But
Well,
it
I know
is,
you've done a lot of time, a lot of work on that. So yeah, okay.
I have seen the comment made that all kids are natural scientists.
Mm,
They want to understand things, they want to explore things, they're fundamentally curious, and that is the essence of science, but it's not the essence of science education, which is
yeah.
something we desperately need to fix. But this is make me data literate, not fix the education system. Although
Hmm.
that's a that's definitely part of the goal. Um, what I'm curious about, when I first met the superstars of STEM when I was nominated in
Hmm.
2017, a lot of them said to me that they hadn't learnt enough about data and enough about coding to really do
Mm.
their research properly, and that it was holding them back. Now I know that you have those data and coding skills. Did you learn them formally, or did you have to kind of pick them up by osmosis, or kind of jam them into your own brain in the cracks of your formal education?
Yes, absolutely. More the latter. So, particularly in astronomy, we are considered the very much the jack of all trades, master of none kind of a scientist, where you've got a little bit of data skills, you've got a little bit of stats, a little bit of observational or experimental design skills, um, and that's partly a consequence of how small the teams are. We just don't, we're getting bigger. SKA is coming online, thousands of people involved, and professional computer scientists are required and data scientists are required to handle the data volumes. Until this kind of era, though, we've been able to get by, and by which I mean, um, you know, well, Python today, I did it at Fortran 77 for goodness sake, which was a nightmare. It wasn't. I'm not that old. It's just that's what my supervisor wanted me to. It was all he knew, so that's all he would teach me, or that's all he would help me in. Right, so I would have to code in that if I wanted his help. So yes, it was very much a learn what you need to solve a problem, and I think that's not a bad way to learn, and certainly it's something that you're going to remember. But I would have greatly appreciated more formal education, and I don't mean necessarily coding. We did a little bit of C at undergrad. This is in Manchester, but the the difference between coding and data science is, well, I mean, it's akin to having the dictionary and being able to be a poet, right? I mean, or a novelist. You've got technically all the words you need as a coder, but to turn
Mm.
that into something that other people were interested, the outcome of which, that's the skill of a novelist or a poet. So I do think that we need to specifically teach that. Now at Swinburne, our PhD students have several units alongside, like coursework alongside their formal formal research program, and it is data science, it is statistics, it is Python coding. Particularly as this field, we have all sort of focused on Python. There's some standouts. Aaron Botham, I'm looking at you over at UWA, who's trying to wave the flag for R, but I think it's fair to say he's lost. The field has moved to Python in the main. Maybe that's our loss. He's very convincing of how the utility of R, particularly for data science. But I think that um, the fact that we can offer our students uh, tailored, well resourced programs of study in data science and in astrophysically inclined data science, as well as in coding in Python, is a bit of a step change. And now you're seeing the last few generations of PhDs being really superstars. I mean, they're just launching into incredible analysis. And I think that that's reflective of the fact that they have these tools that are so polished and so well constructed, because you waste a lot of time if you're just scrambling around on Stack Overflow, and it's it's not even clear what the search term is for, on Google for some of your problems. Whereas, with this, at least you can get rid of 90% of the basic mistakes, 90% of the beginning questions if you've got this structured style of learning. I was unfortunately not one of those students, and I certainly felt that lack. It is a weakness that I've carried through in my career, and I've done my best to try to make up for it. But I can assure you, finding the time for a 40-hour course when you're, doing the stuff that I do now, is, mostly paperwork, that's very hard. So I tend to just continue to limp on and immediately surpassed by my students as soon as they've done like 2-3 months of their work, and that feels okay.
That's the same thing most of the superstars told me, that there's just they can't put their research on pause long enough
Mm.
to build the skills that they need, so they have to sort of limp on, even though it means their research is slower, and it's this kind of terrible vicious cycle.
Mm-hmm.
Um,
If it's actually that's actually a really good structural point. I wasn't sure how many others had felt the same as I. That's fascinating that you've had those conversations. I am a big proponent of investing in people and in technology, investing, uh, knowing that you'll recoup. You will genuinely, as an institution or as a field, you will recoup that investment multiple times over. And it's fascinating that one of the perhaps the cheapest way to invest in researchers is, rather than a shiny new big piece of equipment, would just be essentially free online, but just essentially providing them the time, or at least even just the forgiveness when they then apply for research grants, that there's going to be this 2 week window in their life that's just disappeared. Like, who cares? But until you get that permission to do it as a field, we're never going to invest as individuals until all of us are given permission to do it collectively. And it seems like an outrageously cheap way to get a step change in capability. But yeah, all of us feel like we're on the clock.
well, that's that's an evidence-based approach to policy, which is one of the things that's made
Yeah.
me so passionate about data science, is that,
Hmm.
until everybody has a fundamental understanding of data as a science, and of the ways to, evaluate and really analyze information, that stuff doesn't get valued. And it's such a
Yeah.
handbrake on our progress.
Look, as soon as you can measure something, it's valued, right? That's
Mm.
the flaw in our um, organizational systems. But I think it's also, a truism from a scientific point of view as well. We tend to design experiments to measure what is easy to measure, maybe not what's most insightful. There's a
Yeah.
negative version of that, of course, um, but I do think that having a case study might be fascinating, actually, for us to consider, Linda. But let's take everyone who managed to do the MIT, free online, Python courses or data science courses, and I wonder now, if as a longitudinal study, if there's enough time passed to actually see if there's a difference. But yeah, it'd be very hard to control. You get the people that did that are obviously more mindful about investing in their careers, etc. So lots of design choices that for that program, but it could be interesting to see, just as you say, is the evidence there for how much a help this could be? I wonder. Probably is.
There's a whole sort of rabbit hole I want to go down there with you.
Yep.
But to come back to the podcast for a minute, what is it that you wish everyone knew about data?
Um,
If
that
that
it
was one
is,
thing that you could kind
yeah,
of tell everybody and make sure everybody understood, what would it be?
uh, that it that it has error, uh, both intrinsically, there's measurement error, statistical error. Is there a systematic error? The way in which it's being analyzed and presented to you, are you seeing a true reflection of the final outcome from that with error bars associated? And do you try, in other words, error is everything. It's data can have the allure objective truth. um, and that can't possibly be the case when you have humans involved. There's some subjectivity. Someone's made a choice about what to measure, what not, how to measure it, and all of those things have to be reflected. And I think the understanding of error usually requires some understanding of the experimental or the situational setup. And error is not something that, or uncertainty, to put it another way, is not something that people are particularly experienced with, I think, and is a great source of confusion. We just have to look every week where we get the news poll or any of the other political two-party preferred polls, and you have huge columns written about a 2% swing, and the margin of error is 3%, right? It's like, and mostly that's driven by statistical error. It's mostly that their sample sizes are a few hundred people,
Yeah.
not the 100,000 people you would actually need. So I'm never sure even how they get percentage errors on these things. But so error is the key to understanding the value of the data and anything that's interpreted from it. So I think that's something I'd like people to be better aware of.
I wholeheartedly agree, and it's the first thing that I teach in all of my workshops, that there is no such thing as a perfect data set. And
Mm,
so, your first steps of trying to understand the data set are to ask the question, "What's wrong with it?" Not "Is there anything wrong with it?" What's wrong with
yeah,
it?
that's
Because
right. Yeah, yeah.
there's just no such thing as a data set which is flawless and exactly what you need it to be. And I think that's caused a lot of trouble, or a lot of misunderstandings in the pandemic as well, where
Mm,
as more data comes in, our understanding changes, and just simple things, or things that we thought were simple, like what's the death rate? Well,
mm,
the answer is it depends, because it depends on the population that you're looking at, and the resources available to them, and the state of the health
mm,
system, and there's so many factors that there is no
mm,
single death rate for any disease, and that was something I didn't understand at the start of the pandemic, really,
mm.
and to to give people who are searching for um, understanding and certainty the answer "it depends" is it's quite unsatisfying, which I think leaves us open to the people who say, "Oh, I have certainty."
Yeah, well, this is the challenge that faces most of us in the scientific world, and data science very very firmly in that world, where the appropriate and correct couching of uncertainty on a result or a conclusion, the fact that it relies on other factors or assumptions, that's a hard sell and a soundbite. And as you say, particularly where people are wanting certainty, an uncertain answer doesn't give the comfort that a populist who's able to either you know, by intent or just lack of awareness or knowledge, makes such a clear and bold statement. It is a worry that we get drowned out in the communications. But again, that's not a podcast about pedagogy, education, communication, but rather data science. So I'll stop trying to lead you down rabbit holes.
Well, I think the connection between all of those is so fundamental. You shouldn't be talking about data without talking about communication, because um, it, it doesn't matter how um, valuable the result is that you found if you can't communicate it effectively, and
Mm,
particularly if you can't communicate the limits of that result.
mhm,
And I think that's something, we're taught science as a series of facts. And this is something I go into in a fair bit of depth in Raising Heretics, because when we teach it as facts, when we teach science as, these are the components of cells, and these are the laws of gravity, and this is stuff you need to remember, and it doesn't change.
mhm,
That's not teaching the basis of science, which is we're constantly improving our understanding, and some of these things will change. And
mhm,
when we say these things are laws, sometimes there are exceptions or things that modify the laws, and we're setting people up with the wrong understanding of science. We're setting people up as with an understanding of science as rigid certainties, which is, you know, the
Mm.
antithesis of what science should be.
It is, but to be somewhat argumentative on the point, and I completely agree with you, of course, while noting that the we do have to teach, um, laws, capital L, Newton's laws, and then it was surpassed by Einstein, and we know that Einstein is incomplete because it doesn't include quantum mechanics as GR. Um, so we can we are comfortable and confident relying on uh, certain aspects. It's not that you're not pathologically questioning everything. In theory, you can and should be able to go and double check everything, right? That's the scientific process.
Mm.
But the process in reality is also one of verified trust, right? Like you have
Yeah,
actually seen other papers that have cross-checked each other, etc. That's the field. It's one of constant cross-checking and query, but then it's not pathological in the sense of, oh, I will never believe anyone unless I've done it myself. So I think that
yeah,
that's where we get, I think people with ill intent or not can woefully misunderstand the process of science. It's not one of constant doubt. It is investigation, but as sooner or later, in a practical sense, you have to rely on someone's work, someone's measurements. You factor in the error. If it's a law, you use it, but noting that maybe it's just, if it's something as embedded as GR, then you're pretty confident it's pretty good to better percentage of accuracy than anything you're going to be measuring in most scenarios. So I guess there's a way of saying it's a little nuanced, and I think that there is just um, I think where people become ideologically driven in defining this is a scientific method, I must question everything, can almost become to the extent where they won't believe anyone else. I think that's unhealthy, and that is not actually what science is about. Science is about building on the work of others and being capable and interested and willing to cross-check if appropriate. And so long as someone else or several others have cross-checked, well, then you feel pretty good about not needing to do that yourself, and the field can advance. But there's no hard and fast rules about these things. Certainly something, and it's of course the more important the result, the more it's cross-checked, right? I mean, the idea of in cosmology we have numerous experiments measuring the expansion rate of the universe because it really matters from a cosmological point of view. You're not going to just take one group's work, and I think that that's a but even there you can see that the errors that they've quoted, their numbers are not correct because the measurement of the expansion rate from the other groups, if you look over in time, has bounced around a little, but not as much as the errors that they formally quote would imply. In other words, really, really tight. So in other words, there is a sociological aspect. We are very sure now that we must have, if we see our final number, expansion rates, 70 kilometers per second per megaparsecs, yeah, that's close enough. We probably fixed all the bugs. We found all the bugs, right? So there's a positive reinforcement bias on that, and you stop looking for the problems when you get quote unquote the right answer. And then you're 68 or it's 72, it's okay, But if you've got 80, you're like, whoa. And statistically, one of the 10 groups that year must have got 80. I mean, that's how it must have come out. But they've just gone and found maybe that was a bug that time, or maybe something else happened. Maybe they cleaned the data a little bit more than they should have. Yeah. So you can imagine how that process can also occur. And that's why it's really important that in cosmology in particular, but in any field, the idea of double blinds, we in cosmology, in astrophysics, would add a random number to our data set that we can pull out at the end, and only one person of the team or someone, maybe they get hit by a bus and you're stuffed, but there is that number stored somewhere, such at the very end you've written your paper, and then you're all committed to you found the bugs as much as you can. You're going to submit, that's the promise, and then you take out the random number and run the plots one last time, and bang, that number comes out as the final expansion rate, and you publish that. That's now how we're moving, because we've recognized that even in our own field, we've all questioned and checked each other's work in a data analysis sense, but clearly you can see the way the numbers bouncing around between the results, that there was a some level of uncertain or of unconscious bias creeping in because we would quote unquote know what the right answer was. So there's
Yeah.
it's a bit of a maturing of our field, and I think it's quite a telling one that scientists, we like to think ourselves as independent, but we can be subjective too.
I love that that you're building in techniques to manage our own bias, because I think one
Mhm.
of the most dangerous traps for us as scientists is to think that we are unbiased and objective, because that's not the human condition.
Yeah,
It's not something the human brain can do. We can work towards that, and we can try to maximize it, but it's not the way we think. We are fundamentally emotional, biased, subjective beings, and we
hmm,
if we work with that rather than assuming it doesn't exist, I think we get better results. And it is, it's a matter of choosing the right level, or a decent level of rational skepticism, as you say, not being
yes,
skeptical of everything,
yeah,
and accepting that when 98% of the scientists agree, there's probably something you should be starting
yeah,
to take
yeah.
seriously.
Yeah, I would say
um,
that's not an unreasonable position to take, albeit it seems alarmingly far from universally accepted in our world, which is a bit depressing.
yeah, yeah, it really is. What are some of the worst data mistakes you've seen?
Um, so units is a killer. Units is the classic, and um, we in astronomy have it's actually a running joke of just how awful our unit systems are, and you talk about magnitudes where the brighter the object, the more negative the number, right? That just sucks. But then it's a logarithmic value, so you convert it to linear. But the base, what's the but it's normalized against a certain star's brightness, Vega, for goodness sake, just a star in the sky, and you're like, okay, well, that's great. And then there's others, so there's other conventions that you normalize against other types of stars or some weird average thing. It's a nightmare. So something as simple as literally how bright is the star I've looked at, or galaxy, there's about 5 or 6 separate conventions that you could use, and all of them will trip you up. And
Wow.
it's uh, quite, and very often in astronomy, even today, we will still have DAT files or text files, God forbid, and it's literally just columns if you're lucky. They're column separated. Maybe it's just a complete data dump with no structure, but and there won't be headers, there won't be any kind of comment about what's been assumed, right? So we're beginning to move to a more data mature approach where we've got as much of the conventions, ancillary data, or ancillary statements associated with that experiment, for example, um, tracking with the data itself. And I think that HDF5 is a bit of a revelatory shift for us. We've previously had FITS files, which was somewhat similar. It's kind of the image equivalent. So that was a huge step, and that has been a constant bugbear in astronomy. There's another, which is the expansion of the universe, which is called little h, and it's not a unit. It's technically a number, but it behaves like a unit. I don't even want to get into it. But one of my colleagues
Oh
literally
boy.
wrote a paper called "Damn You Little H." That was the paper title. So again, because of all of the pain that it can cause in terms of correcting or not, and it's very very poorly documented which is your assumption or which is your unit. So those, and you would think that we could when we scan the heavens for galaxies that have lived and died by now, stars that have exploded, outshining the galaxy they live within, we can find all of these things and we still stuff up those numbers. That's pretty bad. But I guess the worst data mistake I've ever seen was no less an entity than NASA, and that was where they were doing the orbital insertion for Mars. It's a number of years ago now, and one team, it's the US, one team was miles, the rest of the team as an international project were kilometers,
Oh no.
and the thing bounced off. the atmosphere of Mars missed its target, right, because of that difference. And
Oh,
we're talking hundreds of millions of dollars, the smartest people in the world, years and years of thought, everything balanced, everything, and it was the simple thing. So you can always look to complex mistakes, or some crazy sequence of anomalies or errors that have compounded and get some bizarre outcome that's just unfortunate. In the main, the vast majority of data mistakes are poor documentation of your units or assumptions or conventions, and and even NASA can get that wrong. So I think no one should feel too bad when they do it themselves, but I think that before you launch into fitting, so some, high order polynomials, or running a CNN on your data, maybe just check it first, eyeball the data, and there is nothing quite like getting into a data file and looking at it to spot the problems. You, from a data mistake perspective, I think it's that you either trust the file or assume that you understand the data, and you start your process, and then you're trying to bug hunt forever more. And it turns out there was just something, you literally open the file and you're like, oh, yep, no, that will be it. There's like minuses there, or there's some missing elements, or some nans floating around, whatever it might be. And I do think that for most of us, we are so keen to get into exploration, problem solving mode, get a quick and dirty answer out. It's the excitement of discovery, and we don't spend enough considered time just methodically cleaning the data. And cleaning doesn't even have to necessarily be changing it; it can just be checking it in that
yeah.
sense. But I think that we never do that enough, because obviously that's not as much fun as training a machine learning algorithm, right? And seeing what it comes up with.
It's not the excitingly techy bit. It's the boring
Yeah,
housekeeping, and no one wants to do the boring housekeeping.
nah, nah.
I'm
We're as
fascinated.
guilty of that. Even where the data is an exploding star, you're still like, nah, I don't want to look at that data. Let's go fit something.
I'm fascinated that you say that even how bright a star is something that is, complicated to both measure and communicate. That's it comes back to what we said at the start, right? That no data is perfect, all data has error, and there's a complexity to data that we just don't really understand a lot of the time.
Yeah, look, it's the particular instances of um, stellar brightnesses. uh, I guess the challenge is because we have such deep intuition, um, and as to say, bias against what a star, its brightness should be, and there's a rich legacy of history in that. We have these historical norms or conventions that we carry with us. No field gets to start again, start clean with this,
Mm.
sensible, quote unquote, sensible kind of definition, and that that's fine. You can you can sort of handle those issues. I guess um, it is just a reflection of both the length of study as a field of science, arguably one of the oldest fields of science, because the night sky was known to all, and was certainly observed by all, and we can um, see in indigenous astronomy the rich history and precision measurements of dating back tens of thousands of years, to know that must have been something similar to the world over. So we have all of these different peoples over thousands of years doing these measurements. Different conventions are going to arise. Okay, more of the European centric versions begin to dominate, albeit through some of the scholars of the Middle East, of Islamic scholars. And it, even then, you still have this bizarre hodgepodge where the French wanted to use this system, and those in Britain would do this, and we move forward to the current day, where we have a we have the potential that all conversions could be done. We have AstroPy as a wonderful unified platform in Python for astronomy, and all the conventions are there, or the coordinate system on the sky. Like, where on the sky is it? Well, it depends where you are, right? Are you on the Earth? Are you on the Sun? Well, no one's on the Sun, but it's a very good reference point because the Earth goes around the Sun. It becomes such a subjective question, and something as simple as, how bright is that star? Where is that star? It really matters that you ask, well, relative to what? Like, how bright
Yeah,
relative to the next star over, the brightest star in the sky, a candle, right? So that's a unit of measurement. So a
the
candela. So
lumens.
so we talk about these different things, and yes, we have CGS units, and yes, they're moving to somewhat. I think will soon be completely dependent on so-called physical constants of nature. Um, but even those might change. So even that's kind of not a done deal. Uh, but the more interesting point is it's sociologically some numbers we're more comfortable or familiar with. We'll use a series of units or
Mm,
conventions that just make it easier for us mere mortals to understand the data, to literally eyeball and see when something is off. And I think it is important that we don't just reduce everything to um, CGS units, right? The question would have been, well, the miles kilometers to back, or there's good reasons why the some of the NASA team are using miles. It's because they've used miles their whole life. They intuitively understand and have a good sense of what that exact number should be. And 5/8 difference with a kilometer, they're going to spot that intuitively, until it was something that was outside of their familiarity comfort zone, which was the distance to Mars. And then no one
yeah,
did spot it because it's a big number either way. So, but I actually have a lot of sympathy for people using units or conventions that ease the initial high level pass. And I'm such a firm believer in getting into the data and looking at the data and having that exploration. And sometimes you've got to do a transformation of the units or a coordinate system so you are familiar with it. There's no point giving me, um, so some other bits of my life in Earth observation. There's no point giving me a a physical image in which the structures which are clearly of the meter scale. There's cars, there's houses, and then having object dat files associated and writing that in nanometers, right? I mean, that's going to that one. Okay, I might be able to eyeball and be able to be smart enough to spot the 10 to the 9 difference. But I think that you would want or giving it to me in angles, right? I mean, I need to physical size of the object. Don't give it to me, oh, it was it was an arc minute. I'm like, what is that for a car? I don't understand what that means. So I do feel that that the data, while we are subjective, we are still, I believe, the best tool to spot weird and unexpected mistakes, or even quite simple mistakes. But it's very, very hard to programmatically detect and clean identify. You just the Don Rumsfeld, the unknown unknowns.
yeah.
And quite frankly, even the known unknowns are a pain to try to programmatically try to search for as well. So I do think that we can be forgiven for wanting data in a format that's more familiar to us and our frame of reference. It just eases the exploration, albeit it comes with the risk that you'll stuff up the units, the conventions later on. And when you try
Yeah.
to do your, real physical measurements, that it might actually go a bit awry.
A part of the issue too is that the weird result is sometimes not an error. The
Mm.
weird bit of data is sometimes the result that you're looking for, or some totally new thing that you haven't considered before. So that that challenge of what do we do with outliers is a perpetual, that no right answer kind of situation, and quite
Oh,
complicated.
look, well then that, I mean, that really the outlier, the classic, I think it was, is it Arthur C. Clarke quote? The most interesting sound in science is not eureka, but that's curious. It's that slight puzzling difference, and you begin to investigate it ever more. And one beautiful example in data was the measurement by Penzias and Wilson, where they were looking at the sky in radio waves, or microwaves, and they were getting some noise, some anomalous amount of signal after they removed everything. So they went and they checked every electronic joint. They went and they did a different scan pattern. They went and they got into the large radiation, even cleaned up some dielectric material, as they phrase it, which is pigeon poo for the rest of us. So they literally cleaned this thing beautiful, um, and still this anomalous amount of power was detected in their data, and wrote it up, being the exceptional investigators, experimentalists that they were able to show, here's our data. We've done all of these tests. We've done absolutely every check. This is a rock solid result, but we don't know what it is. And then independently, the prediction of the expanding universe was it started off hot, expanded, and gets ever colder. By the time that fireball, the Big Bang, reaches the size of the universe as it is today, it is sufficiently cooled in the expansion of the universe to now drop from crazy crazy hot gamma rays, or whatever, ultraviolet, down into radio. So in other words, they were picking up the afterglow of the Big Bang, and it was coming from everywhere on the sky, and that's it was one of the most beautiful experimental results, and so precise and robust was their experimental design, and so unfailingly um, rigorous in their analysis of their data, that they were willing to publish something that they just didn't know what it was. And of course, I mean, clearly it was a mistake. Clearly there was a loose wire somewhere, right? Well, except when it wasn't, and it was actually the afterglow of the Big Bang. So I think that's a great example that the unexpected, the outlier in this case, in terms of power, it's extra 2.7 Kelvin on zero. Like it's a tiny, tiny amount of signal, additional signal. Um, if you truly trust and understand your experiment and all of the ways in which it can go wrong, and you've corrected for everything, and you still have a signal, well, sometimes you just got to publish it, and hopefully someone else will figure out what it was that you were seeing, but you at least were convinced that the thing you saw was real.
That's just magical. Have you ever seen data deliberately misused?
Hmm. Um, so, not misused in my field. One instance where it got a bit hairy, though, there was a claim of the detection of primordial gravitational waves in this afterglow of the Big Bang. Um, would have been Nobel Prize winning. Crazy implications. And an experiment called Bicep 2 did this result, claimed this result. And it was staggering. I mean, it was immediately that came out. Obviously we would then go check, but everyone's like, well, okay, I guess we know who's won the Nobel Prize this year. Literally probing the universe back to the trillionth of a second after the Big Bang. It's the most exquisite implications. And then people started to investigate the paper and the results. And how did they get these measurements? And one of the critical implications, or critical uncertainties, was that they're seeing the afterglow of the Big Bang through the galaxy, right? We're in the galaxy, we have to look through it to see this afterglow of the Big Bang, which is coming from all around us at the very furthest observable edges of the universe. Seeing the universe literally as it was back then. The light's been traveling to us for 13.6 billion years ever since. And they had taken data provided by someone else of the map of that of our galaxy, and in particular the dust, literally the dust in the lens of the camera in this case, albeit dust that's literally floating in space, and that was, I mean, that was okay. It wasn't great. No one was loving that bit of the analysis. Immediately, that was assumed to be, if this could go wrong, it would go wrong here. Um, just the dust can mimic the signal. But then it got really bad because the measurement of the dust was by a team that hadn't published it yet, but they'd given a preliminary talk. The Bicep collaboration, someone there had taken a picture of the presentation on
Oh
their
no.
phone. They zoomed in, they digitized that to try to get the dust map, the what's called the power spectrum, but the some higher order kind of analysis on that, and that's what was fed in to then what would be one of the biggest discoveries in history. So it was not good from the start, and it got worse the more we got into the analysis and the revelations behind, and so it wasn't. I don't know. It wasn't a great example of data analysis. I mean, just on a practical terms, it's quite a clever, use of modern technology. But you know, is anyone who's actually looked at image analysis on phones? Huge amount of algorithmic work goes on behind the scenes to sharpen up to make it look nice, right? You don't know, you can't trust it to that level, not to a degree of that we will then try to claim we're seeing the trillionth of a trillionth of a second after the Big Bang. So horrible stuff. And of course it was wrong. Of course it was the dust. There was no signal there once actual other telescopes began to cross check, and they had to retract
Yeah.
it. It was a huge embarrassment. And it was, I guess, it spoke to um, how important the scale of the discovery was. And instead of driving us to be more careful as a field, it drove us to be more ambitious, to push the boundaries of the data analysis, um, arguably inappropriately.
Yeah.
Rather than us being more careful, the prize was so big, there was more ambition, and
Yeah.
corners were cut. And I think that that's a salutary lesson that I certainly use in my own research groups. And I remind people, new students, about this example, because it is such a. By the way, the team, extraordinary researchers. Absolutely, the Bicep team are just some of the best astronomers you've ever seen. But just goes to show what can go wrong when the pressure gets too great.
Well, it is, it does come back, doesn't it, to that idea we talked about before, that scientists are human, and
Mm.
all of us have had the experience of getting too excited about something and going in, headlong and mucking it up just out of sheer enthusiasm.
Yes, that's, and to a certain degree that's certainly understandable and forgivable. I guess all of us as a field thought it was pretty off. Taking a
Yeah.
picture of a clearly written preliminary do not use result, and then trying to get the scoop anyway, and stuffing it
the,
up in
the
the process.
the levels of outrageous there are so
Yeah, it's pretty.
numerous,
That
it's
one was
hard
pretty
to.
crazy. Yeah. That sets the standard. That's for sure.
Yeah, you can understand the enthusiasm, but perhaps not the execution
Mm.
so much. Um, we are probably running out of time, and I could honestly talk to you all day if you give me the opportunity. So I want to wrap up with one last question, which was not in the questions I provided to you. So it's not a trap, but it's just one
Which,
that I
and
was thinking
again, in
about as you were talking.
yeah, we'll complete peek behind the scenes on this for any of the listeners. I didn't actually read those questions either, because I'm that poor as a scientist in preparation for my interviews. But yes, let's go
That's
on.
good. It
So
makes
this
it
isn't going
makes
to
it more
surprise me any more than
spontaneous.
the other questions.
What excites you about data?
ah, um, there's always this sense of discovery, or at least the potential for, and I think that is. Um, the idea, and certainly if it's data for the first time that no one else has seen, right? Like there's that unspoiled wilderness, the exploration. You genuinely get a little bit of that emotional sense from going into the data, and obviously it helped. The context is everything, right? I mean, if you're giving that data
Yeah.
and it was the stock market, okay, well that might be modestly intellectually interesting, and I'll be like, okay, that's great. I found this trend, and oh yes, it's been well known that, I don't know, stocks in the morning get traded less than later. I don't know, whatever the correlation. Vastly more exciting, of course, is if it's something about human behavior or my own field of astronomy, whatever it might be, and but either way, they all have that sense of possibility, and you might discover something new and heretofore unknown. And any scientist has that drive to explore the uncharted, the unknown. That is something that keeps us going, and often can keep us going through years of work, of dedication to one program of work. I mean, Sabre is, I think I've been in that now for 7 years, and hopefully soon it will, we'll get the answer. But in the hunt for dark matter, but the idea of just any data file, you genuinely have that sense of discovery awaiting you, and that's always gives me a little buzz.
What a beautiful note to finish on. Thank you so much, Alan. I really appreciate your time, and this has been an awesome talk. I really enjoyed it.
Ah, Linda, thank you so much for having me. Thanks you for the opportunity to pontificate about data. Rarity is a wonderful opportunity.
Thanks for listening to Make Me Data Literate. You can support the work of the Australian Data Science Education Institute at givenow.com.au/ADSEI. Tune in next time for more conversations with amazing data experts.